Okay, so this lecture is about parallel operation of generators. So we look at the requirements, the reasons behind why we operate generators in parallel, as well as any possible, say the requirements, then means by which we measure, or before we parallel generators, what we are supposed to do. The characteristics of generators when they are operating both alone and in parallel with other similar generators, as well as the dynamics of operations within a large system. And we'll do one or two examples of the same. So let's get started. Right, so when we have a set of generators, there are certain advantages to operating them in parallel. So operating them in parallel would mean that you have more than one generator in the same area, two or more, that you would be able to link together and be connected to the same set of loads. So the advantages of this type of setup would be, first of all, a greater load can be supplied. Obviously, if you have a 10 MVA load, you can supply it with a series of 1 MVA generators. Secondly, you can have greater reliability of the system. This means that if any one generator would fail, you are likely to be able to still manage to supply at least some of the load because of the other generators that are connected. Whereas if you only have one generator, you'll only be able to supply as long as that generator is functional. If it goes down or if it has any issue, you would not be able to supply the load. And that leads us to the third one, which is the ability to maintain. So maintenance is possible while the generators are running. So again, if you have a bank of 10 generators and you need to pull one out for maintenance, depending on your load, the rest of the generators would be able to run continuously. You do not have to disconnect your loads in order to serve maintenance. And another advantage is the ability to manage supply and efficiency. This is to say that all generators that are in this type of situation you would only run those generators which are needed for the load. So like if your load is variable or it varies with time, you would only switch in generators as they are required. Have that set of generators running.
Excuse me, sir.
Yes.
There's some people who are asking to be let into the class.
Okay, let me just check.
Thank you.
All right. Welcome, the ones who have just joined us. So we are talking about the advantages of parallel operation of generators, which are as listed there. Yeah. So as I was saying, you are able to manage your supply, or you manage the amount of generators that you have, and you only run them as and when they are required, and that improves your efficiency. So what are the requirements in order to connect generators in parallel? So there are a number of requirements in order to have your generators running together, connected to the same load in parallel with each other. So firstly, the phase sequence must be the same. right? Phase sequence means the order in which the red, yellow, and blue phases reach their peaks must be the same for the system that you're connecting to and for the generator that you wish to connect to that system. They must be running in the same order. So if your system that you're connecting to is red, yellow, blue, your generator that is coming in needs to also be red, yellow, blue. If it is opposite, there will be currents flowing in between the generator and the system instead of going directly to the load. Secondly, terminal voltage must be nearly the same. So if your generators are running at 11 kV, it should be approximately that voltage. So if the system voltage is 11 kV, your generator should be operating at close to that. This will allow it to match up with the system when it actually joins. And number three, the frequency must also be nearly the same. Just letting some people. Frequency must be nearly the same. And number four, there must be no phase difference. Right? So the phases between them, that is the power angle or power factor, should be the same with the system that you wish to connect to. So at this point, it would be useful to introduce the concept of an infinite busbar, or to remind you of the concept of infinite busbar. So this is defined as a three-phase supply with a constant voltage and frequency, regardless of the loads that are exchanged. So it's a three-phase system with constant voltage and frequency. Right? This is because you have systems that have so many supply generators and so many loads that the voltage and frequency are extremely stable, such that the addition of one more generator would not make a difference to the voltage and the frequency. As we will see going forward, you remember we talked about voltage regulation. That is when a generator is supplying a load. If the load increases, there's a tendency for the voltage to dip. So in the case of an infinite busbar, your generator, if you connect a generator to that system, or even if you connect a load to that system, the system is so large that it will not be affected in terms of voltage and frequency. You can supply or demand as much as you wish from that system. The other concept that we want to introduce is synchronization. So synchronization is the adjustment of the speed and frequency of a generator when it is being connected to a system. So in order to achieve synchronization, you need to meet all the requirements that we have listed here. So when all these requirements are met, the generator is said to be synchronized to the system that you want to connect it to. And like we said, a system can be another generator or a set of loads or even an infinite busbar, which is the equivalent of a national grid. Let me admit a few more. Any questions so far? I think this is pretty clear. Okay, so what are the conditions for synchronization? We've listed them here. You need to have the phase sequence to be the same. The terminal voltage must be close. Frequency must also be close. And the phase difference, the power factor, should be roughly the same. It should be close enough so that they are not too far divergent from each other. So how do we identify if a generator has the right phase sequence, first of all, for connecting it to another load. So let's take this illustration. So you have generator 1 supplying a load, and you want to connect generator 2 through switch S1. So we assume S1 is connected together so that it switches at once. And you want to check what is the phase sequence, or is it possible to connect to that system. So your system consists of generator 1 and the load, and your generator that you wish to connect is generator 2. Now we would have the setup as indicated here. So you'd have lamps. These are lamps connected across the switch. So one, can I call it a leg of the lamp, would be connected to the system voltage, and the other would be connected to the generator voltage. The assumption, of course, is that your generator is running at the required frequency and voltage and ready to go. But you just need to check the phase sequence of what is there. So how would we go about this? If the phase sequence is opposite, so like assuming this phase sequence is red, yellow, and blue. If the phase sequence was red, blue, yellow, which is the opposite of the phase sequence, these lamps would light up out of sync with each other. So they would go bright and dim in different instances, right? So if lamp 1 is bright, lamp 2 might be off, lamp 3 might be a bit dim, and so on. So in order for you to ensure that they are in the same phase sequence, the red, yellow, and blue, you would exchange 2 terminals, either of any 2 of the 3 terminals, you exchange them so that you now have a correct sequence that matches. So if you have a correct sequence that matches, you will see that the 3 lamps will light up and dim together. Now the lighting up and dimming is not due to the peaks and troughs of the sequence itself. The lighting up and dimming is because if we take, for example, the phasors of the system, say generator 1, the system generator 1, if those are the phasors, which is red, yellow, and blue, your generator 2 would be in a similar way, because they are connected in 120 degrees opposite to each other. So R, Y, and B. We've already assumed they're in the same phase sequence, so they match each other in terms of the phases that they have. So if you were to superimpose the phasors of each of those, assuming 120 degrees all across, the direction of rotation, the phase angle of generator 2 may be slightly faster or slightly slower than the existing generator 1 phase angle. That would mean, in terms of the phasors, it would appear that if we assume generator 1 as the baseline, it would appear that either generator 2's phasor is moving away from generator 1, or it is moving slightly towards it. So if it is faster, it is moving away, say in an anti-clockwise direction. If it is slower, it is moving towards it, say in a clockwise direction. And it is that difference, because if you look at this circuit, this is the equivalent of your red from the main circuit, and this is your red phase from the generator 2 circuit. So your lamp is connected across these two, right? And your lamp here is also connected across these two and across those two. So what the lamps are actually showing is the phase difference between the two. So as long as there's a phase difference between the two, there will be some voltage circulating between them. So the aim of checking the phase sequence is to ensure that you can see that brightness or dimming going in the same sequence, right? So let's look at it a bit more in terms of proper synchronization. So when you have synchronization, now we have a slightly different setup, still with 3 lamps, but you can see they have been set up slightly differently. So this illustration shows the wiring for a setup which we want to connect to. So let's say you have this is our generator 1. Let's call this infinite bus bars. And it is part of a system that you want to connect to. And you want your generator 2 to connect to your system of infinite bus bars with your generator 1 already running, right? So in this case, you now have what we have shown. So if this is the phasor of your infinite bus bar in red, right? Your infinite bus bar, which has a generator 1, is in red color over there. And the incoming generator, generator 2, the phasor is in the blue color that we are seeing there. So what you're seeing is the phase sequences are matching each other. So red to red, blue to blue, and yellow to yellow. And the incoming generator seems to be slightly ahead of the infinite bus bar, right? So there's a phase difference in between the two. So now if we look at how the lamps have been wired, so you have this lamp 1 is connected between the red of the infinite bus bar and the red of the incoming generator. So lamp 1 is in between the two like that, right? Then you have lamp 2, which is connected between the yellow of the infinite and the blue of the incomer. So yellow of the infinite and the blue of the incomer. So it is there, lamp 2. Okay. Then you have lamp 3, which is connected between the blue, which is there, and the yellow. So it goes through here to the yellow, right? So you have lamp 3 is connected in between those. Of course, the phasors, the diagram is a bit counterintuitive, but it should show us what we want to see. This L2 is not supposed to be here. It is actually supposed to be. L2 is between yellow of infinite and blue of, so this is actually L2. Sorry about that. And then you have L3, which is connected between blue of the incomer, yellow of the incomer, and blue of the, it is actually like that. So incomer, yes. Okay, so it's actually like that. Fine. So you have those 3 lamps connected in that phase sequence. Now, we said that the incoming generator is either slightly faster or slightly slower in terms of the phase angle than the infinite bus bar that it is going towards. Okay, so it will either be slightly faster or slightly slower. So it's tending to go backwards or to go forward, clockwise or anti-clockwise. In this case, lamp 1, if we have the, let's just pick one. So we pick one that is, we are moving forward, right? So it means that all these phases, the blue ones, that is the incoming generator, the ones that are colored blue, are all tending away from their counterparts within the infinite bus bar. So red in the incoming is faster than red in infinite. Blue in the incoming is faster than blue in infinite, and so on and so forth. So what that means is, as long as there's a gap between the two, there's a voltage between each of them. So for L1, lamp 1, what will be seen in lamp 1 is that you have, it will start off as dark and go towards bright. All right. So if in the initial sequence it was nearer to red, the incomer here is nearer to the infinite, it tends to move away from it. So the difference in voltages between the two is increasing, meaning the lamp is getting brighter. The lamp indicates visually the potential difference between the 2 points where it is connected. In the case of lamp 2, we now have it is getting dimmer from maximum. So initially it is far away from the yellow, yeah, but because the incomer is moving towards it, so it appears to be reducing the potential difference between the two. So it is from a maximum brightness to dim, right? And then L3 will be it is brighter and even becoming more bright because it is moving away from its counterpart. Okay, so bright to brighter, right? So those will be the sequences. So it will start, at the instant before this moment that is depicted here. They will be as indicated, and then they will tend to move brighter, or the lamps will become brighter or dimmer according to the sequence that is indicated. When we have achieved synchronization, we will be able to note that the difference, this speed of angle, the movement away from the movement away from each other between the incoming phase and the infinite busbar, you will have matched them so that these will remain stationary. So the idea would be to match them such that there is no phase angle between them. All right, you would want to match them at the point whereby they have rotated, and the red, this red in the incomer, is matching the red at the infinite busbar. So you would want to tend to have it moving at that point. And at that point, when it has reached, of course, you will find that lamp number 1 will go off, and then lamps 3 and 2 will be fully bright at the same brightness. Okay, so at the moment of synchronization, lamp 1 is off, and lamp 2 and 3 are at same brightness. Okay. Now, of course, this poses the problem that how would we be able to note that? How do we fully indicate? Now, this was a system that was in use. It's a fairly easy system to put in place, so you would run into it in some places. But nowadays, of course, in the area of digitalization and so on and so forth, generally what you would find is a machine called a Syncroscope that automates this process. We won't go into how it operates, but generally a Syncroscope is a meter or some kind of indicator instrument that literally shows you if your generator is fast or slow, and you would need to either slow it down or speed it up to match the positions of the infinite busbar that you want to connect to. I may not have mentioned that the process of synchronization, of course, involves speeding up or slowing down the generator's prime mover so that it is matching the speed and frequency of the busbars. Okay, so that's mainly it about synchronization and the conditions for which we require in order to run generators in parallel. Any questions so far on that? If there are no questions, we can move on. So let's look at some of the characteristics of generators when they are operated in parallel. So before we go into that, our first instant will be generators operating singly. So singly operating generators, right? So generally, and I will take you back to what we talked about the last lecture we met. Generally, you would note that in terms of a voltage that is supplied by a generator. At the end of that lecture, we said that as electrical loads vary, the voltage is maintained by changing excitation. And we said that out of all the things that we will learn within this unit, the most important is that one, that the voltage of a generator, the voltage is related to the field current or the excitation. In terms of production of power, all right, the power that is generated is dependent on the prime mover, right? So the prime mover is the one that controls power and at the same time frequency, right? Power and frequency are very closely tied to each other, and they are mainly manipulated by the action of the prime mover. If you need to supply more power, and here we are talking about real power, active power in particular, not just apparent power, active power. If you need to supply a greater load, you must put in more from the prime mover. This makes sense in terms of physics, in that if you are, lifting some load and the load is 100 newtons or whatever it is, you must be able to put in to the motor as much power as is required to carry out that work. The same thing applies to generators. If your load requires 50 kilowatts, you must have, the prime mover must rotate the generator in such a way that it can produce 50 kilowatts, right? So the energy put in must match the energy being put out. And at the same time, the prime mover is the one that determines the frequency by determining the speed. So one additional thing that we would want to include here is that while the prime mover affects active power and frequency, the excitation of the machine or excitation of the generator affects the voltage as well as reactive power, or Q, right? And IF, or excitation, in practical generators is called the voltage regulator system, right? And on this side, active power, or the prime mover, is regulated by the governor, right? So these two are the main means by which we alter the operation of the generator in terms of the loads that we need to supply. Let me admit somebody to the class. Oh, I've just seen there's a question. How bright or how dim is the gauging? Say if you're new to the equipment. Yeah, I think I mentioned that the problem would be, unless somebody had experience, they would not, it would be difficult for a layman to see straight off what the lamps are doing, or to identify what the significance of the brightness of the lamps would be. Yeah, which is why there's now the improved use of synchroscopes. So getting back to this, yeah, so when a generator is operating, those are the two key elements that you will need to take care of, or you will need to remember. Always remember, the voltage regulator varies voltage and reactive power. The governor varies active power and frequency. Let's try that again. Okay, so having known that and having said that, let's now get into how generators operate as the loads are varied, all right? Because this is all about the characteristics of generators when they are working under load. So now let's first of all look at the active power being regulated by the governor. So the action of the governor is such that when you have a speed at no load compared to a speed at full load, you would tend to have a droop or a drop, which is called speed droop. All right. Governors are set up such that they give a linear relationship between the speed and the power that is being supplied. And that relationship is usually known as speed droop, right? And you will now see that the relationships between these ones are both linear. On the other hand, let's move this to this side. It is matching where it's supposed to be. So that's on this side. And when you look at the relationship for a voltage regulator, the same thing applies. So voltage regulators ensure that there is a linear relationship, and this is controlled by varying the field current. Okay, so in both cases, so in the case of power, you will have power is equal to SP into no load frequency minus frequency of whatever system there is, whereby the power is, this is active power or generator output. This is now a slope of a characteristic we will see shortly. This is your no load frequency of the generator at that particular set of generator settings. And you have system frequency, the frequency of the system that you are supplying. Okay, so now let's look at what those characteristics look like. So you can see side by side we have the two relationships that we were talking about. Here on this side we have your real let's call it active power, and on this side you have reactive power. And those are the relationships between the two. And you can see that you have a slope SP that determines the characteristics of the reaction of the generator to any change in the load. So you see, for example, what we have mentioned before, the droop of speed, right? The generator at a certain power, when it is applying a certain power FL, let's say the full load power, it will be at a frequency that is given by that. As you go decreasing the amount of power that the generator is supplying, the frequency of course will increase, yeah, naturally, because of the characteristics of the governor. So the governor keeps that relationship in a linear form. Okay, so what you will then see is that if you would require certain power to be supplied at a certain frequency, you need to have a different value, not a different value of SP, but a different value of F at no load. Okay, so what do we mean by this? We mean that in case you want to supply power, a certain power P, let's say there P1, but you want to supply it at this frequency, yeah, under the governor settings that you have. So this slope is given by the governor settings. We call them set points. Under the set points that we give in this, that result in this slope, your full load power will be at a frequency of here, FFL. But if you still want to have that frequency, but supply active power at a lower level or even at a higher level, you would then need to change the set points, and you would have a line that goes slightly like that. Okay, my line is not very accurate. Try again. Close enough. Okay, so what you would do is you would then have a new value of no load frequency at which you would set your governor. All right? So what that means is, if, for example, imagine that your governor is running without being connected to any load. It is isolated, it has been disconnected from everything. It is just the prime mover rotating the alternator, and you're measuring the frequency that is coming out of the terminal points. At no load, at zero here, when you're supplying no load in those conditions, you could then set the governor to adjust the speed that it is outputting, right? So at zero, instead of running at, say, 1400 hertz, it would be able to run, say, 1400 RPM. You could run it at 1300 or something like that. And by dropping it like that, you drop the entire line to a lower level such that you can supply your P1 at the frequency that you desire. This is what we call governor set point adjustment. Okay. Normally, when it is running, you would not touch the governor set points. These are predetermined. However, if you want to now adjust, you can do so. Okay. So the governor set points that you put will determine if the load changes momentarily, very small load changes, they will change along this line. So the frequency will alter along this line. That is why if you stand next to a generator, for example, when it is first switched on and you have a load applied, you will hear the frequency of the sound dropping. It is an actual change because the governor is changing, it's doing its job of changing the position of the frequency to match the load that is being supplied. However, if you have now longer term load requirements, that's when you can change the actual governor set points. The same thing would apply to our supply of reactive power. So if you want to supply reactive power at a value of Q1, say with a terminal voltage that is predetermined there, you would then be able to change the values of the voltage regulator. So this is voltage regulator. You change the values of the voltage regulator so that now it has a different, same slope, but it has a different starting point. Yeah, remember this is just y equals mx plus c. It's not a curved line, it's just not able to do a straight line at the moment. Okay. So you would then have the same slope, but starting at a different point. Okay. So those are the characteristics of the governor and the voltage regulator. So once again, governor is prime mover speed, and voltage regulator is field current regulation. Remember, with field current, we had a resistor, a variable resistor that was changing the value of field current, which in turn changed the value of induced internal voltage, which in turn affects the terminal voltage, which is what we are looking at in terms of these characteristics, right? So we go back to what we have said before. The voltage and the reactive power are controlled by the voltage regulator in terms of excitation. Active power and frequency are controlled by the governor in terms of the motion of the prime mover. Any questions so far? Okay, so let's move to do an example. The figure shown shows a generator supplying a load. The second load is connected in parallel to the first one. So here we are not looking at parallel operation, we're just looking at single operation and the changes that will occur to frequency and terminal voltage when we change the load in a generator. So this is quantifying what we've just talked about, the linear characteristics of generators in terms of active power and reactive power. So you have a generator with a no load frequency of 61 Hertz. That is the set point that you have set for this particular instance. The slope is given by 1 megawatt per Hertz. So for every megawatt increase, there's a 1 Hertz drop in frequency, right? As per the characteristic that we had. Load 1 consumes that power at that power factor, and load 2 consumes a real power of that at a power factor of 0.707. Before the switch is closed, what is the frequency? After the load is connected, what is the frequency? And what can we do to restore the system frequency to a desired value? Right, so let's look at that. So first of all, before the switch is closed, what is the operating frequency? So we have a number of things that can assist us in knowing that. So you know that power is equal to SP into FNL minus F system, right? So if we rearrange that, we will get F of the system is equals to FNL minus power over SP. So simply put, you have covering the, yes, I am. Sorry about that. Okay, so keep it over here. So then we have what is the value of those? So we have FNL is what, 61 minus the power initially. So the power initially is 800. Sorry, it's 1000, not 800, 1000 over 1 megawatt per hertz, right? So this is equal to 61 minus 1. It's actually equal to 60 hertz. Okay, so that's the initial. After load 2 is connected, you then have the system frequency is equal to the same thing. We've not changed the set points, but the power has changed. Yeah, instead of 1000, we have 1000 plus 800. Okay, so it is this 1000, and then you have the real power of 800. So the two of them would be 61 minus 1800. So 1000 plus 800, 1 megawatt. The reason for the change is this is in kilowatts and this is in megawatts, right? So you can actually subtract them. So minus 1.8, it gives us 59.2 hertz. Okay, that's after connecting load 2. So essentially what we've said is you had your initial load over here, but at a certain, when we connected P1, it traveled backwards and the frequency, we increased. So the initial one is at this point, and when you add, it now moves down to that point. Say this is P2, right? So there's a drop in frequency from here to here, right? That's the frequency drop that we've talked about. So from 60 hertz, it has dropped to 59.2 hertz, because for every megawatt increase, it drops by 1 hertz. So what would we need to do? Yeah, here what we are talking about is what we had discussed on this point. We want to run this generator at this set point, okay? So if we look at it diagrammatically, you have your set points looking like that. So you had your P1, which is 1000 here. Then you had P2, which is 1000, P2, which is 1800 at that frequency, right? So frequency 1, this is frequency 2. So frequency 1 is 60, frequency 2 is 59.2. Okay, this is at no load, this is 0. So what do you need to do in order to get the machine to operate or to supply 1800 kilowatts, but at a frequency of 60? So you need to change your set point such that the P itself is at this point, right? Because you want to operate at 60 hertz. You want to bring it back to 60 hertz that we had in the previous example. So what we then do is what we talked about, the set points. So you will change the governor set points from this to this. So this is set point number 2, right? This is done by changing the governor, right? So for short term, you know, when you have a load suddenly increased, yeah, it would travel along the machine itself, right? Along the characteristic itself. It would not shift in between. For longer term situations where you know that is the load you're going to supply, you would then add or change the set point to match the situation that you would like to have. Okay, so that's the basic characteristics of machines: voltage, reactive power done by the regulator, active power and frequency done by the governor. So let's look at another situation. So let's look at a generator connected to an infinite bus. So what happens when you connect a generator to an infinite bus bar? So reminder, the infinite bus bar is a 3-phase supply with a constant voltage and a constant frequency. Regardless of the loads that you are supplying to it, you will always get the same voltage and the same frequency. There is no droop. So if you were to draw it, the infinite bus bar would have a characteristic that looks like that: frequency and power. So whatever power you put to it, it will retain its frequency steady. Same thing with your reactive power, Q. Whatever reactive power you draw from it, whatever you want to tap from it, the voltage will remain the same. Okay, and this is the characteristic of your infinite bus bar. But a single generator does not work like that, of course. So what happens when you connect a single generator to an infinite bus bar? Okay, so let's put them side by side next to each other, and they would look like that. Okay, this is what we call the house diagram. So in the case of power, you have on the left hand side the diagram of the infinite bus bar, which is introduced at that point. And on the right hand side, you have your generator that you want to connect to the infinite bus bar. So for the infinite bus bar, whatever power is there, frequency will remain the same at this value. But for your single generator, remember it has the governor droop characteristic. So it will vary along that line. So what you do in the case of a generator which you would like to connect to an infinite bus bar, that's what we talked about, synchronization. You have to alter the characteristics of the incoming generator to match the already existing infinite bus bars. So in case your generator is supplying power to the infinite bus bar at that level, if you want it to supply at that level, at a new level here, so call it G2, PG2. Let's call it P2. The droop characteristic will not allow it to match. It does not match. Here is where your generator wants to be, but your frequency of your system is over there. So in order for you to match the two, you then have to see what is the point at which you want to supply at. You want this power to at this frequency F of the bus bar. Let's call it FE. Your no load frequency is here. Okay, so you change the governor set points to match that value. So you have set point 2, right? This is original set point. So what this tells you is that if you want to introduce or you supply an infinite bus bar, whatever amount of power you need to supply to that infinite bus bar, you have to adjust your governor to meet the frequency that is required. Okay? And the same thing would apply in terms of reactive power. You would have to match your infinite, the terminal voltage of the infinite bus bar to the reactive power that you need to supply. Okay. So now let's go a bit deeper into some of the conditions that will be faced when you're trying to connect a generator into an infinite bus. So first of all, we look at how do you change the generator set points, or what happens when your governor set points change without a change in the voltage or the field regulator. Remember, you have both of them on the same machine. So initially, you would have, if we look at the phasor diagram for your generator. Now, if you have current at unity power factor, it means that you would have it at that point. So let's match that point, right? So EA and VT, assuming a unity power factor, right? Now, what we would then encounter is that your internal voltage, when it is connected now to this infinite bus bar, if you want to supply power at this point, you are supplying a certain value of PG. Right? At this point. In the terms of the phasor diagram, we usually demonstrate power on this axis and reactive power on the horizontal axis. So the vertical is active power, the horizontal is reactive power. Let's shift this a bit. Let's put it here. Okay. Now, in this particular case, if we change the governor set points such that you are now supplying a power that is higher, so let's say you are supplying at PG2, right? That means that your terminal voltage in this case will remain the same, okay? Because you're connected to an infinite bus bar, yeah? Your machine has to remain at that terminal voltage, but you want it to produce more power. What options do you have? You then have to have, with this, the internal generated voltage, you then have to change the value of the internal generated voltage. But remember here, in order to change from PG1 to PG2, we have changed your governor set point. Okay, you change that. But we are saying what happens if we change the governor set point, but we retain the voltage regulator. All right, you change governor set point without changing voltage regulator. If you do not change the voltage regulator, what does that mean? Internal generated voltage remains the same in terms of magnitude. So what are the constraints that you have? You then have, similar to what we have seen before, if your internal generated voltage can only remain the same in magnitude, you then have a locus that looks like that, roughly. I can draw an arc. It's not helping. Okay. So what that means is, in order for you to achieve PG2, you'd have the same value of EA, right? This is EA1. Same magnitude, but now you have a different value of IX, okay? And that means that, consequently, your current, your current here as well will kind of change, IA2, right? Your current will change to match the change in those. So what this means is, if you change the governor set point, if you want to supply more active power, but you don't want to change the excitation, what would result is you have now the power factor of the generator will change. You will now have a more leading power factor. And if you increase the power even further, your current will move more towards that direction. It will be more leading, and you will have more the power factor change, right? So what this practically means is that if you increase this, you are now consuming reactive power in order to increase the governor set point, or to increase the amount of power that you are supplying. Okay, an increase in the amount of power being supplied without changing the field excitation leads to consumption of reactive power. So in that case, how do we change the reactive power so that we then have at least an increase in the power factor, and you return it back to unity? So I will try to demonstrate that on this same diagram. Try and delete some of these. So put this here. Okay. Now, right. So if we have, I'll zoom in a bit. If we have your system looking like that, okay, so we have increased our power from the initial point, which is PG, to PG2, but we realize that we are now consuming reactive power. Our power factor has gone off. So we want to return it back to this point, which will enable us to have the PG2 that we want, but at the same time, we will have a good power factor. So that would then mean, let me put it in a different color. So that would then mean you have your EA3 now moving across to PG2. How do you achieve that? You notice that this EA3, the magnitude has now increased. So it brings us back to what we had talked about, that the reactive power is varied by the voltage regulator. And what is the voltage regulator? Voltage regulator is IF. Okay. Remember that EA is equals to K phi omega. And phi is related to the field current that we have. And field current, of course, is your voltage regulator, right? So what we have done here is we have managed to increase the amount of power, but we have still retained our power factor where it is. So that means that you have to regulate both the voltage and the governor, the prime mover, together in order to achieve whatever values of power and reactive power that you need to achieve. Okay. And incidentally, our current here related to this IX3 would be, sorry, it would be somewhere there, right? So an increase from IA to IA3, okay? Because you are now producing more reactive power, okay? Instead of consuming, we have now started producing. Right? Okay. So in summary, for a generator operating on an infinite bus, there are a number of things that we need to take into consideration. Okay. So generator on infinite. So number one, frequency and voltage are controlled by infinite. All right. When your generator is connected to an infinite bus, you cannot change the value of frequency and voltage at which you supply. You must match those values because they are dictated by your infinite bus. Number two, the governor set points control active power. We've seen that already here. If you want to go from PG1 to PG2, you need to be able to change the value of the governor. You need to change the set points that you are applying. And then number three, the field current controls or voltage regulator controls reactive power. And we saw that over here, whereby in order for us to change the power factor at which the machine is operating, we changed the current, which changed the value of flux, right? These things are all related to each other. Okay. So now let's look at another instance. This is now generators of similar size. Okay, in parallel with each other. So here we are looking at if you have loads like that, you'd have a generator 1, generator 1 connected to the loads, and you would then have a generator 2 connected to these same loads. So what are the characteristics when you have these two generators operating next to each other? So for infinite buses, we had the house diagram looking like that. But now here we have a case where you have two generators, each with slopes. So what are the dynamics of those two kinds of generators? Okay. For now, we will assume that they are of a similar size, so they'll have similar slopes and characteristics. Okay. So let's look at how the house diagram would look like. Question? Okay. So you have, instead of your infinite bus, you have your generator 1 with power on this side and frequency on that side. Okay. Let's call that generator 1. Shift it down a bit. And then we have on this other side generator 2, so that you have them back to back. Okay, with a slope going from that point. Now, in this case, the two generators themselves have certain characteristics when they are supplying loads. The first of these is that the power supplied by generator 1 plus the power supplied by generator 2 must be equal to the total. Okay, that is a condition that must be achieved regardless, right? As long as the loads have a certain value, the sum total of the power being supplied by the two generators must be equal to those loads. Yeah, in terms of electricity, whatever is generated must be consumed. Okay, so that would mean that if you have your generator supplying the two loads, and let's say supplying them at a given frequency, you would have, let's say, P1, all right, operating at a certain frequency, F1, okay? if generator 2 is connected in between these ones, it must operate at the same frequency and the same voltage, which means that this frequency is what your generator will be operating at, all right? And it means that consequently, your generator 2 will supply that much, okay? Because they are operating at the same frequency, they must be able to supply the same amount, okay? Now, if there is any change in the frequency, the generators themselves must be able to match this change in frequency. So if I was to take, let me see if I can shift the balance slightly. If we were to shift it and we want generator 1 to supply more of the load, you notice that your frequency is dropping down to match generator 1. However, it has gotten out of line with what generator 2 is supplying, okay? What that means is you then have to have your generator 2 adjusting its set points so that they will match the power that needs to be supplied, okay? So you have your original set points, then you have set point number 2, okay? So you would have to alter, because that relationship of PG1 and PG2 must remain the same. This total load being supplied must remain the same, and you would have to alter either one or both of them to match those characteristics, okay? Similarly, you can have a similar discussion about the reactive power being supplied, so that you have that. So this is Q, this is G1, this is G2, okay? So similarly, the amount of reactive power being supplied has to add up to a certain amount. So if this is QG1, this is QG2, sorry, G2, your terminal voltage there, it is operating at a certain V1, okay? If we were to change the values of those, and we shift it along, say, up to down here, right, down here, okay, that would mean that you now have a second value of voltage, V2, and you need to also have another, straighter, then need to have set point 2 for your voltage regulator, right? And that matches the two of them. So you have QG2 and QG1 being the total reactive power that you're supplying to this system, okay? So in summary, for generators that are in parallel to each other, okay, so the key points for generators that are in parallel. The first key point is total active power and reactive power supplied must equal the total loads. Let's call it consumption of loads. All right, that is rule number 1. Then from there, number 2, in order to change the ratio of power while F1, the frequency, or rather, in order to change frequency, you have to have constant power, okay, which is demonstrated here. So number 2, to change power with constant frequency, we must change governor set points. And number 3, to change frequency with constant power, the same applies. You change again set points. Right? Which was demonstrated here. Okay. So we needed to have changed all of those in various ways. Number 4, in order to change reactive power, Q, with constant voltage, VT, you can increase the value of the set points, and you increase on one and you decrease on the other in order to match the two. Increase, decrease. We will demonstrate all of this shortly. And number 5, in order to change VT with constant Q, we increase one, change, decrease other. So let's go through these one by one. So starting with here, right? So you have your diagrams as listed here. So we want to change the ratio of power. So let me change some of this. Right? You have your house diagram that looks like that. Okay. So initially you have, let's call this P1 and this is P2. Okay. But you want to retain the constant, the frequency being constant, right? So what do we do? Yeah, you want your frequency being constant, but you want to change. You want P1 to produce less, say, you want it to come here, say P1A, right? So let's see how that would look like and what we would have to do to achieve that. Okay, so what we want is we want to retain them at the same frequency, but you increase the value of power being supplied. So this means that you would then have to change both frequency or both set points. Delete this one. Right? So you had your initial set points there, but now you need to have a new set of set points here. Okay, so in this case, you are decreasing your set points, but in the other case, you are then having to increase, right? So in order to maintain the same ratio of P1 to P2, yeah, supplying the same load, remember, the sum total must remain the same. So that value has to remain the same. In order to keep the same frequency, you'd have to decrease the set points of generator 1, but increase the set point of generator 2. So that's the case number 2 that we've written here. To change the power with constant frequency, change the governor set points, as we've indicated. Increase one and decrease the other. This other one, to change the frequency with constant power, we have to also change the set points. So let's look at how those set points will look like. So let's say you have your F2 here, and we want to then change it. So let's remain with only the values that we are looking at. Clean it up a bit. So let's say P2 is here. Let's simplify the diagram a bit. Right. Let's say your generators are running at that level. P2 is there and P1A is where we left it. So in this case, we've said we want to change the frequency with constant power, right? So P1 and P2 remain where they are, but we want to increase the frequency. So in this case, we will then have, you want your frequency to increase, but your powers to remain the same, right? So your powers remain where they are. You want your frequency at F3 instead of F2, right? So frequency goes up that direction. What you will then have to do, of course, is you change the governor set points of both in order to meet the new frequency demand that you have. Okay, so what we then see is, in order to maintain the same power but increase the frequency, the set points of both have to be changed. So instead of saying change, let's say increase. So increase. And this other side. So to change the power with constant frequency, increase set point of 1, and decrease the other. And here we increase set points of both. Right? That is to change the frequency with a constant power. You retain the two powers that you want. The ratio remains the same. So let's look at now for reactive power. So in case you want to change reactive power and retain your voltage, what do you need to do? So once again, let's clean up here a bit. I want to change Q with constant VT, right? I think let's give ourselves, yeah, okay. So this is Q. Oops. This is Q G1. This is Q G2 A. That point, that point. So we want to retain the voltage as the same point, but we want to change the ratio of reactive power being supplied. So let's say we want to decrease what is being supplied by generator A. Voltage remains the same at that point. So in this case, QG1B and QG2B, right? Once again, set point there and set point there. So what you've seen is similar to what we had seen before. Your set point, one of them goes down, one of them goes up, right? So in this case, you increase one and decrease the other. And in order to change VT with constant Q, so let's change the VT with a constant Q. Let's keep our new value. We want to change Vt with constant Q. So the value of Q in this case remains where it is, and we raise the voltage. Let's call it somewhere there. And we now have same values of Q that we had already instituted, but now you have a different voltage from voltage T1 to voltage T2. Now have it over there. So of course your value of set point is over there, and another one is over there. So in this case, both of the set points in the voltage regulator have increased. So actually what we've said here is you don't increase one and decrease the other. You actually increase both or decrease both. Let's say change, because it can be an increase or a decrease. Change both set points together. And similarly here, it's not increase necessarily, it can be just a change. It can be increase or decrease. So let's change. Okay. So those are the impacts of various types of power changes to systems that are either with infinite bus bars, working alone, or working with two generators next to each other, right? So generators in parallel require certain changes. So essentially, in order to match the loads, rule number one has to be the power being supplied must match the load. Okay, and this applies to both P and Q. So both active power and reactive power. So Q of G1 plus Q of G2 must be equal to total load. Right. And this is made even more complicated that, of course, you will be supplying these powers and active and reactive powers at the same time. So essentially, you must play with the voltage regulator and the governor, prime mover governors, at the same time in order to achieve these instances. So what we will do next, in the interest of time, I will just leave it at that. Look for example 5-6 in your text. This would be, what is the name of that text? I'll send it over as a note in the classroom text, but just look at that example. Make sure you go through it. It's pretty straightforward. If I get a chance, I'll just upload the working out, but you can be able to follow it. It is similar to what we've done before with the, let's look at it. Is it here? Yeah, it is similar to this example, uses the same principles, the power and the slope, but instead of having one generator, now you're looking at the dynamics between having two generators operating at the same time. So have a look at that example 5.6. And we'll be able to start something new in the next lecture. So thank you very much. Any questions at this point?
Excuse me, sir.
Yes.
About electrical machines design.
Yes.
Which reference books can you recommend?
Oh, I had recommended, there was a text. It was called Electrical Machines Design by Agarwal. I had mentioned that one is available in the in the bookshop, but as I say that, I've remembered bookshop might not be available. I don't know. Okay, very similar to that. Let me just check. There's another book that I got that is quite similar, not as clear, but it is quite similar to that. I think I'll upload that because it has similar text. But as much as possible, if you can find electrical machine designed by Agarwal, because that is the main basis of electrical machines design, that section of this unit. So I'd really encourage you to look for that. But I'll post, there's another one, an alternative, electrical machine designed by Rajini. That's an alternative that you can get.
Thank you.
Wambua Michael, why did we choose the graphs to be on the opposite sides of the vertical and also one to be lagging and the other leading? Okay, why are the graphs on the opposite sides of the vertical? I'm assuming you're talking about the house diagram, Michael, if you can clarify your question. Oh, the house diagram. Okay. It is a way of comparing the two. It's a very good graphical way of matching them up to each other because starting with this, what you're seeing here, you have the characteristic of a single generator. Then we built on that and we said for an infinite bus, you then have the infinite bus having this characteristic. So in order to match the two, remember we are talking about how generators can work together. So the two options are either you have generators of similar size working together, two of them, or you can connect them to an infinite bus. Infinite bus, excuse me, has that kind of characteristic. So when you put the two together, you're able to graphically explain how the two would interact together. So like for example, with the infinite bus bar, you already know on the left-hand side, you have your infinite bus bar, and you can project it onto the right-hand side where you then set up your generator with its characteristic. So it's a way of superimposing the two characteristics on the same axis so that you can graphically explain things like the last part which we've talked about, which is kind of this sort of thing. Yeah, if you have them back to back like this, you are seeing the way I was moving around the ratios and increasing the frequency. Graphically, that's how you would do it. The example that I've talked about now puts that mathematically so that you can use the slopes of each, because these slopes, these values of SP, you will generally have the value. So like, for example, say, 1 megawatt per hertz or something like that, whatever it will be, right? X megawatts per hertz. Okay, so now when you're comparing the two of them together, this graphically represents what you're talking about. And second part of the question, also one to be lagging and the other to be leading. What do you mean? Michael? The slopes are on different orientation. Meaning you're asking why they're on different sides. Yeah, I think that's related to what I've said, that it's a way of diagrammatically showing them.
Excuse me, sir.
Yes.
I think he's asking, you see, is it arbitrary, as in the visual representation is almost like one is lower than the other?
Oh,
Yeah.
no, I mean, okay, it was for the sake of demonstrating. So, like, for example, let me redraw it somewhere here. So, like, if you have, let's say you had one, it's a terrible diagram. So let's say you had one on this side, yeah? So this is your generator one. with its power characteristic there, and that is its frequency over here, right? At this point, this is your frequency no load for generator number 1, okay, at this particular set point, all right? For generator 2, I mean, it's for purposes of explanation, it was arbitrary. We can match them if we want, whereby F at no load of generator 2 is the same as the one for generator 1. All right. The point is, in order for you to match the two, you would be changing the set points of both of them to match whatever situation you have. That's what we're saying. It's the example will be able to show it a bit better once you go through the example, because it is mathematically shown.
Oh, and also about the slopes, one seems to be negative, the other positive too. It's also about that.
I mean, you can have them on the same side, but it is easier to have them opposite to each other. It's not that it is negative, it is that it's kind of reflected on this side. You're putting them back to back. So in order for you to have them back to back, you would have, yeah, I get what you're saying. You know, one appears to be negative and the other one is positive, but it's for purposes of graphing them. So like if you had, you know, if it went back into leading, it would go like that. Whereas this is, I don't know if you get, yeah. It's for purposes of showing them next to each other. You could also even superimpose them one on top of the other, but graphically this looks similar. That you're able to draw this thing, you know, and you show P1 and P2, and you'll always be able to ensure that the total distance between these two will be your total power consumption, right? If you were to superimpose them with the slopes on the same side, you wouldn't show this visually. You wouldn't be able to show this visually. Okay. Okay, if there are no further questions, we will end there. And we will meet again next week. I think this is the last. I'm not, oh no, there's still a couple more about synchronous generators, so we'll do that next week. Then after that, we'll start on synchronous motors. Then we'll go back to machine design. Okay, thank you very much. That's the end of the lecture. We shall meet again next week.
Thank you.